Okay, so the next speaker is Ramesh. He's a professor of computer science at University of Southern California. The floor is yours.
Thank you, Jenny, for the introductions. So today I'm going to be talking about some methods to formally verify SDN control planes. And this work is led by Purya and Arvind. They're co-joint authors. They couldn't be here, so it fell upon me to give the talk. Now, we all know that network control planes essentially determine path availability. So they determine network paths, and the way they do this is by translating intent to network state. And they also update network state in response to events. And collectively, this network state on all the switches determines the paths. And when you have path unavailability can impact service availability and can impact the ability of large cloud providers to adhere to availability targets. Now, unfortunately, control planes can have bugs, right? And I'm going to walk you through a very, very simple example that may seem like a toy one, but it actually ends up being pretty real. So this example relies on an orphaned entry in switch A of this topology. An orphaned entry is something that exists in the switch, but the controller doesn't know about. Now, in this topology, traffic is going through B from A to D. And when B fails, the controller actually updates the network state and thinks it's done the right thing. Unfortunately, with the orphaned entry, the traffic still goes through B and gets dropped. And so this inconsistency, we call this intent state inconsistency, results as due to controller bugs. And these bugs can often be extremely subtle to find and fix. Right? But they're not hypothetical. So we did an analysis of open daylight commit logs over a significant period of time. There are several examples of these kinds of bugs. I will also argue that these kinds of bugs are unlikely to go away because control planes are evolving to become more complex. Today, microservices-based control planes contain several independent microservices that coordinate through the neb, right? And the advantage of this is that now you have significant concurrency, right? So you can scale to larger networks. You also have the ability to independently evolve these microservices, so it provides faster velocity. Now, the downside of all this is that these controllers are actually prone to lots of bugs. You might imagine, as many of you who work in microservices know, race conditions are all too common. But now the controller has to reason not just about switch failures, but also component failures. And many of these failures can be concurrent at scale as the network scales. Now, of course, there's a realization that it's very hard to do away with these bugs. And so many of these controllers have a procedure by which they can resolve these inconsistencies using a process called reconciliation. And reconciliation is this basic idea that you retrieve state from all the switches, you compare the state against the intent, and then you repair the inconsistency, right? And you do this periodically, and this works just fine. So in the example that I showed you, the graph on the right shows what happens to the throughput of the flow from A to D. And the red line shows what would happen in a controller with periodic reconciliation. So there is a certain amount of network unavailability, about 10 seconds in our example, before reconciliation kicks in, resolves the inconsistency, and then the throughput is restored. What we do in this paper is produce before I go there, I wanted to mention that basically this approach eventually matches intent to state. And what we do in this paper is propose an idea called ZENITH that essentially can recover the throughput much faster than periodic reconciliation. And the way it does this is by, instead of recovering from inconsistencies, by avoiding them entirely. Okay. And the way it avoids this is by ensuring intent state eventual consistency, the same property that reconciliation gives you. It does this by avoiding this by construction. Now, what that requires you to do is to be able to formally specify and verify the controller. Okay. And once you go down this path, you're faced with a few challenges. The first of which is, how do you even get a specification of a microservices-based controller? And how do you verify it? To that end, we have developed ZENITH Core. This is actually a provably correct microservices-based controller. And I'll be talking mostly about this in the talk. There are two other contributions discussed in the paper. The second of which is, even if you have a correct controller, you still need to verify applications so that you can get end-to-end correctness guarantees. And to that end, we have developed ways to verify SDN apps very quickly. And the third contribution is, even if you have a correct specification, there can be bugs introduced in the process of actually implementing that specification. And so, to that end, we've developed a code generator for specifications that generates a complete implementation. As I said, I'll be talking about the first contribution and spend most of my time on that. Now, ZENITH Core is a provably correct, eventually consistent controller. And when I say ZENITH Core, I mean all of the components in red in this picture. And there are three questions that come up in the context of getting to a provably correct, eventually consistent controller. I'll describe each one of them in turn. But before I do that, I need to give you some background on a framework for formal specification and verification that some of you might know about. It's called TLA+. In TLA+, you specify distributed systems using temporal logic, and then you can verify and prove properties. Now, the TLA+ is a rather extensive framework. I'll give you the basic mechanisms that you will need in order to understand this talk. The first element of TLA+ is that you need to express these correctness conditions that you're interested in terms of logic formulas. And the formula on the right is an example of such a logic formula. The second is there is a programming language for these specifications. And so, as this picture shows, this is a declarative language that allows you to specify. It's called PlusCal. In addition, TLA+ has a model checker for verification and a proof system for proving correctness. Now, let's take the first question. What determines controller correctness? Now, in order to express these correctness conditions, you need to be able to express intent-state inconsistency. And you want to do this in a logic formula, so you need mathematical representations of intent and state. For state, the mathematical representation is relatively straightforward. It's a sequence of operations and switches. For intent, the mathematical representation that we've come up with is a directed acyclic graph of network actions. And this graph captures the dependencies between operations that you might want to perform on the network. And think of it as a lower level intent representation. To help you understand what that is, look at the picture on the right and imagine that there is traffic flowing through B from A to D, and now you want to drain that switch. You want to remove that switch from the network. Now, in order to do that, the corresponding DAG that you might generate is one that installs the new path first, and then removes and then that should be delete the old path. Now, once you have these mathematical representations, you can design the right correctness conditions. And the correctness conditions are things that ensure that you never violate the dependency. You always install the state that is specified by the DAG, and you always make sure that the nib in the SDN controller is consistent with the network state. Okay. Having done that, the second step is how do you actually specify a microservices-based controller? And to understand what that is, I haven't even told you what our microservices-based controller looks like. It's actually fairly complex, but the part that we're interested in, again, is within the box on the red. And I won't go into most of the details, except to point out that it contains two things. It contains these microservices, each with individual components, all of which then the components can execute concurrently. And now, lacking any controller specification, how do you even come up with a specification in the first place, right? The way we chose to do this is by actually systematically developing the specification. We started by first developing a monolithic controller, no internal concurrency, but it has all the functionality that you would need. Then we decomposed it into the microservices, verified it, decomposed each microservice into components and verified it. As you might imagine, each step added significant complexity to the verification, which I will get into shortly. But the way we did the verification was we verified this using the built-in model checker. We injected failures, and then we fixed the specification errors and repeated. Now, we injected several kinds of failures, the first of which is a set of failures on switches. And of these failures, we emulated complete failures, transient as well as permanent failures, as well as partial failures of the switch, where you might lose the routing state, or you might lose a component, but the routing state is preserved in those variants. The second set, which is unique to these microservices-based controllers, is the failure of individual components. So this is what I mean by partial failure. So a single component within a microservice fails and restarts again. How do you recover from that? And how do you ensure correctness in the presence of that? Unplanned failover, which is when a microservice fails because, let's say, a power outage and a backup takes over. And planned failure, which you want in the case of planned failover, which you want in the case of maintenance operations when you want to migrate a component from one machine to another. Now, the model checker interleaves these failures arbitrarily and concurrently, and it also models partial and transient failures. The advantage of systematically developing this specification was that it uncovered several subtle and very deep errors, and I'll give you an example. But the paper also discusses several common design patterns that result from specification errors, and also ways to efficiently fix them. And efficiency is something that I haven't gone into in this talk, but is important for high throughput controllers. So here's a very subtle specification error. The x-axis shows time, the y-axis shows all of the different components in the controller. At the beginning of time, a switch goes down, and you see the events as a result of the switch propagating up through the controller to the app. Now, this is a transient failure. The switch comes back up again, and you see another set of events going over the network. Now, while each component is working independently, the model checker observed that if you were to delay one of these components significantly, that could result in a bug. It could result in a component actually rewriting the nib so that it would result in a situation where the network has some state that the controller doesn't know about, the orphaned entry that I told you about. Now, as we went through the process, we discovered that the Zenith core specification is significantly large. It's about 2 to 3 times larger than previous specifications, and model checking by itself doesn't scale. And so we ended up using a bunch of scaling techniques, most of which are pretty standard, but we had to adapt them to our setting. Now, even after doing this, you can only model check modest input sizes, modest topologies, modest DAGs, and so on. And so there's no guarantee that the resulting specification is actually correct for any possible topology. And so to ensure that, we took the third step, which many people don't, which is actually proving the correctness of the specification. And so the figure on the left is supposed to show the PDFs of the pages of the proof. The proof is about 4 or 5 pages long. But the basic idea behind the proof is that you identify some properties that you assert of the specification. Then you prove the correctness, you prove by contradiction the correctness of the specification if all the properties hold. And then you take each property and you prove it using the TLA plus proof system. And so this is discussed in the appendix, and you're welcome to take a look at it and be happy to talk about it offline. 2 other contributions have to do with the fast verification of the apps and the code generation. And again, I haven't gone into both of these. I'll end by discussing a couple of results, both of which show that Zenith converges faster than reconciliation, which is the problem that we set out to solve. The first experiment did a trace replay. Recall that we found a bunch of specification errors as we were verifying the specification. Now, we took the two controllers, one, the traditional controller with periodic reconciliation and with ZENITH, and we made them go through the set of states that resulted in a bug. With the periodic reconciliation, you always get an inconsistency. With ZENITH, you get no inconsistency, and of course, ZENITH converges faster. The x-axis on this figure shows the different traces that we use. The y-axis is the convergence time in log scale. And you see that the convergence time is, for ZENITH, it's about an order of magnitude lower. We also did experiments just to demonstrate that ZENITH scales to a very large testbed. We did an experiment on a 600-node testbed with random concurrent and switch and component failures. And so this hits controllers pretty hard. So you're always injecting concurrent failures. And what happens with PR is that it's sometimes inconsistent, but ZENITH is never inconsistent. And you can see the difference. The graph is a CDF of convergence time in seconds. So to conclude, I started by telling you a little bit about the importance of network availability and how reconciliation resolves inconsistency post facto, and we wanted to avoid inconsistency in the first place. And there are lots of things that you have to do. It's fairly involved, but the end is that we have a core, provably correct core, and ways to ensure end-to-end correctness of the specification. And we've released some of the specifications, the code generated, the generated code, and so on at this GitHub repository, and I'm happy to take questions.
Thank you. Any question? I'm going to start with, oh, there was, sorry.
Hi. On one of your slides, you mentioned that you reduce the microservices to subcomponents. And I'm curious, what are the rules or based on which you do the reduction to subcomponents?
Oh, so what we wanted to do is design a controller that looked exactly like today's controllers, and they have that structure. So they have microservices, and within that they have some parallelism, and that's what we want. That's why we wanted to take that step.
Okay, but you don't look inside the microservice to reduce it even more to subcomponents.
No. So the controller, if you go back to that picture that I had, let's see if I can go back to that picture. So you have each one of these microservices, which is that thin red box out here, and within each one of these there are these independent components.
Okay.
And so the first step is to decompose into these two microservices, and then the second step, or the third step, sorry, is to decompose into these individual components.
Okay, thanks. Thanks for clarifying. Thanks.
Any other question? I do have just one. I'm curious.
Of course.
There were someone? Okay, go ahead.
Just a quick question about when you say that you have to handle modest constraint and specification, do you have some specific limitation about that? I mean, in the scalability of the problem, when you have to formally check the specification with respect to the implementation?
Yeah, so when you're formally model checking the specification, you have to give it some input topology, and you have to inject some set of failures and so on, right? Now, if you give it a very large topology, the time to verify blows up significantly. And if you give it a complex operation for which the DAGs are pretty large, it takes longer to verify. And so all the optimizations that we did, it brought down the time to verify, but it would still take hours and hours if you increase the topology size. And so then the question becomes, okay, now what happens when you scale to a data center topology? Are you sure that the specification that you have is the model checked specification is still correct? And the answer is we can't verify that experimentally, and so that's why we ended up proving.
Okay, and do you have some way to create a pipeline in which you have new specification, you start to check them, and then maybe you can update while you are still checking if the server is too large?
There are ways. We have, in addition to all of the optimizations that we described, we use model checking parallelism and all of that. And even so, it's harder to scale to very large topologies.
Okay,
And the primary reason is just that the specification is extremely complex.
Okay, thank you for the answer.
Then there is no more time. Thank you very much.
Yeah.